Hello, Prof. My name is Anthony, and I'm going to be presenting my ECE 106 design project, capacitance-based near-field rainfall detection. So first off, I'd like to start off by apologizing if the audio quality is poor. I will try my best to edit the audio so it's loud enough, but I did lose my voice trying to record this yesterday, so hopefully this time you can hear me okay. And secondly, I'd just like to start off by saying that this report is going to be split into three sections. One is going to talk about our design philosophy and sort of how we chose this project. The second part is going to be talking about how we calculate the capacitance. And the last part is going to be how we integrated the circuit and how we designed the circuit to measure capacitance. And there's a fourth part, which we won't be able to see today. I'm still waiting on a shipment from China with my PCB. So once that's here, I will append the video as I mentioned to you in the email. All right. So the first part, as I mentioned, is going to be our design philosophy. And we can look at a few different things when we consider why we picked this project. So the first thing we looked at is existing rainfall sensors, right? Because we had this sort of inspiration from the ECE 106 design document. What kind of rainfall sensors are there? So there's resistive sensors. These usually come in Arduino kits or like Raspberry Pi kits. And essentially, as water droplets hit traces that are exposed, it shorts or it increases the number of pathways for the circuit to connect, and you can measure capacitance that way. So these have the issue that they're exposed to the elements and they're not really durable, right? And in our scenario, we want to create something that's durable and that'll last and that won't be accidentally hit like a rock and just break. The next one we have is rainwater collection, and we saw a few different videos on this already, right? Where you have two different plates, and as it fills up with a dielectric of water, the capacitance changes, and this has some of the same issues as the previous resistive sensors. They are also exposed to elements. They also are very difficult to mount when you're in like a moving vehicle, because if I'm moving and I have to collect water, it can be really difficult because momentum wants the water to leave my car. Let's say if I stop or if I go, and there's no real way to get over the NVH part of having a hole in your car to collect rainwater, right? And there's no way for you to properly manage the rate of ingest of water and the rate of like egress of water when you drain it out. So it could just fill up and just never drain, right? And it's hard to tell in that sense. So it's not really good for a moving vehicle, which is the primary design for this. The last one is optical rainfall sensors, and I have one of these on my car, and there's a few issues with it. One is that it can easily be blocked. Sometimes there's a leaf in front of the sensor, and it thinks that it's raining really hard, and also it only works on this small area of my window, and this is pretty universal for most vehicles. And they basically scan the small area of the window, right? So if that part of the window is dry and the rest of your window is really wet, your wipers still aren't going to turn on unless you tell them to, which is not really automatic. Same thing in reverse. If that part of the window is really wet, like someone just spilled coffee, then the wipers will go crazy, but the rest of your windshield could be totally dry, which is going to have adverse effects on not only your mental state because your wipers are going in when you're trying to just drive, but also it could have lasting effects for your actual wipers as there's no water to actually lubricate the wipers when they're wiping. Okay, so now we go into the sensor design, and there's multiple different ways to actually design sensors to use fringe fields for measuring capacitance, right? But I'm only going to present two of you here because, well, they're the only two sensors that I could have made, and they're the two sensors that I think I could have done calculations for, like approximations for, right? And obviously later we'll couple this with circuitry, but on the left we have the finger design, on the right we have a circular design. And both these two designs, when you look at them, essentially what it is you're trying to get electric fields perpendicular from your traces to go across and meet up with an oppositely charged traces. So in circular design, it's similar to a parallel plate capacitor, and it's like a cylindrical capacitor, except there's many rings and it's in a 2D or almost 2D shape. And then the fingers design, you basically have parallel plate capacitors, but they're really wide and they force traces. And there's just two traces that are, one is positively charged and one is negatively charged. And in circular design, you could have alternating positive and negative charges. Okay, so now we talk a little bit about fringe fields and Coplanar capacitance. So we know already that our design is based off of fringe fields, right? And we've briefly covered fringe fields in our ECE 106 lectures, and we've also seen them a bit mentioned in multiple different textbooks. So like Feynman's lectures, and we have also our textbook from ECE 106, they all mention fringe fields, but they don't really tell us much more about that. So in the top right, you can see my really poor drawing of fringe fields. I tried my best. And then we also have this concept of coplanar capacitance is what happens when you open up a parallel plate capacitor. And this is something that I heard about from micro antenna design and like from like radio wave transmission. But I think it's a really cool topic to investigate, and I thought it was going to be pretty relevant to what we're doing, because essentially what we're doing is we're looking at a whole bunch of flat traces and asking electric fields to go between them. Okay, so I've talked about this really briefly earlier, but we're looking for a change in capacitance in the fringe field, right? So as our water, which is going to be our dielectric, enters this fringe field, it's going to change the way the electric field interacts with the plates, and that's going to decrease the electric field, decrease the voltage, and increase the capacitance, right? And this applies for fringe fields because it's just electric field lines that we're interacting with essentially. And this is something that's pretty common in touchscreens. I know my microwave probably uses something like this, and I know that a lot of older laptop trackpads also would have used something like this. So that's the idea behind what we're trying to achieve. Is we're trying to change the capacitance in some fringe field so that we see a result. And we can then lead this into our final design choice, which is going to just be what we call fingers earlier, right? And there's a few reasons why we picked this. It's easier to design and manufacture and prototype. It's easier to design because I just have to draw straight lines. It's easier to manufacture because circles are always going to be harder than straight lines because most machines go in X, Y, and Z, although this probably isn't an issue for large PCB makers. And it's easier to prototype with because I can actually attach two traces to the two traces, or two wires to the two traces using contact pads without having to attach multiple wires to each individual ring and make sure that they're all connected together properly. And another reason is I thought it'd be easier to approximate capacitance. So obviously straight lines I think have always been easier to work with. It's easier to integrate over a straight line than it is to integrate over a curved line. Maybe this isn't actually going to be the case when we try to calculate capacitance, but in my mind it was always easier to approximate capacitance in straight lines, and straight fields are easy to work with, and I would rather parallel plate capacitors than like cylindrical capacitors. And there's two more points we have to mention. One is that it theoretically has a wider sensitivity area. So you can see in the bottom right that there's simulations for different designs. And this was for like proximity capacitance array sensors, like touch screens or touchpads or sliders and stuff. And you can see that different designs will have different sort of areas of effect. And we want to have an area effect that's as wide as possible, obviously, because we want to maximize the area we have. And the last one that's not on the slides is we actually picked the design before we'd done a lot of the calculations. So once the design project we knew about a month and a half ago, when we formed a group and we came up with this idea, I sent in the PCB to be manufactured using whatever data I could think of just off the top of my head at that time, because I knew it would take about a month and a half to manufacture and ship to me in Canada from China. And unfortunately, we see the effect of like these shipping delays. And so the final prototype that we have may not actually be the most optimized model. It may not work at all, but nonetheless, I'm excited to present this project and I hope it works, and I'll find out when it gets here. So now I'm excited to bring you into the second part of my presentation, which is calculating capacitance, or I would rather say approximating capacitance, because I'm going to present three different methods I try to use to approximate capacitance, and they're going to vary from really bad to maybe passable. And these are all different methods that we've tried to use to get a general sense of what a capacitance is, and you'll see in the calculations later that maybe some of them didn't work as well as we intended to, but we use concepts we learned in ECE 106 to try and do our best. So that leads me to my first attempt at calculating calculating capacitance. And we know that like capacitance is roughly defined as Q over EDL, or like Q over delta V from one plate to the other. So I also know the field from a line charge. So I try to do this integral from one finger to another because we can approximate our fingers to be infinite line charges, and we can integrate along the path to approximate capacitance. Turns out that this integral is actually really complicated to do, and it's really hard to do. And I don't really know the path that they're taking, and I don't really know any approximations that I can use to help calculate this integral very nicely. So this attempt didn't work out super well, and maybe I'll come back to this once I know some more math and know some more theory. But this is the first attempt we made, and if you want to see the math for it, I can upload it in the PDF document for you. So now we have the second attempt, which is the approximation on fringe fields. And what you see here is my attempt at approximating fringe fields. And obviously this is basically going to have the same issue as before, because I really don't know how to actually integrate across this like curved area with my electric field, because there's so many different factors at play, right? And then, so this prompted me to like, okay, I don't know what I'm doing. I need to find like a textbook or a resource that I can use to get a better handle of what is going on. So we get these different numerical methods for approximating fringe fields. And these are presented in a bunch of different like sort of books and journals and like resource pages. So there's a bunch of different methods, and like obviously they all look pretty similar except for Palmer's formula, which I think even then is pretty much the same idea. They just have different coefficients near the end. And I thought it would be really cheap to use this without understanding at least the approach that they took. So let me explain this to you. They take a conformal mapping from the edge of the parallel plate capacitor and then turn it into essentially what is a straight line. So you'll see that they move it from like an XY plane to an omega plane, which is math beyond what I know how to do. But apparently it works out for them, and they get this like really nice equation, and they can then do your like V to V very simply, and you can just get the capacitance from that. And it makes sense except for the part where they do conformal mapping. This is a math that I tried to figure out, but I couldn't. And this conformal mapping especially was really complicated because for some reason they didn't start just at the edge of the capacitor. They actually started further back on the capacitor. So there were flat plates of the capacitor that also had to be included, which made it a little bit more complicated than I think it would have been. So regardless, we know how it works. It's the same idea as always. They just use some more fancy math to get it, the approximation. And we can take one of these formulas for sensitivity analysis with parallel plate fringe fields, and we can find an average capacitance for our two dielectrics, air and water on each side. Okay. Now, knowing that there's this method to sort of adapt from one plane to another, we take a look at coplanar capacitance, and we draw these electric field lines in this really beautiful way to make them circular, and we can then describe them in terms of R and theta. And obviously, that's going to be a lot easier to integrate if we can turn that into some form of like integratable area, right? And later on, we're going to see that actually this is doable, and there's some math that needs to be done for this, and I don't know if you want to see it or not, and I don't know how long I should spend on it, but I've included it anyways just to be safe. So the first thing is we need to have this like Laplacian operator, which is seen in ECE 106 and we've seen in the textbook. We just need it in polar form. So we do a lot of this to get it into polar form. You see here we do chain rule and we do like differentiation to get it into polar form. And then we can write our electric potential in this form, and we can then get electric field as a gradient of the electric potential, and then we can get capacitance, which is just amazing. Actually, we don't get capacitance right away. We got the surface charge density because that derives from the electric field and like and I've used just an epsilon here. I know in the textbooks they use like epsilon naught, epsilon r or something. Epsilon here means the exact same thing. Hopefully that's clear. And hopefully we can see the math pretty clearly. I added in a step in the middle, which might be extraneous, where we actually showed the integration of the two lns, because like obviously it's a mathematical or like algebraic property of a ln where ln a minus ln b is ln a over b, but it wasn't super clear at first, so I've added that one in, and you can then see the capacitance is just q over v, which is what we've done so many times. Okay, perfect. Okay, so now that we have our method of getting capacitance or approximating capacitance with coplanar capacitors, we use the same dimensions that we had before. We have a finger length of 5 centimeters, a separation of 3 millimeters, and a width of 5 millimeters. And actually, no, sorry, a separation of 5 millimeters and a width of 3 millimeters. And we plug that into our equation twice. On the left side, we have it for air, where E is going to be around 1.006, and on the right side, we sub it in for water, where E is going to be around 80. And we can see that we have two capacitance values here for one pair of these like coplanar capacitors. And at the bottom of the screen, you'll see, or at the bottom middle of the screen, you'll see the subtraction or the difference between the two, and that's our change in capacitance. And that's important to know because when we tune our sensitivity for changes in capacitance, we want the change to be noticeable, but we don't want it to be out of the bounds that we can measure. So this is here for reference, and you'll see on the next slide why that's sort of important. Note also that these capacitances are really large, especially the one for having it filled with water, but it does make sense because if you put in this into the water, you're submerging the entire thing. So it seems reasonable because I guess the water is infinite, but I haven't been able to test, and hopefully it's not that large when I actually get to measure. Now we can all do this. Before we get into the graphing, we can do this thing where we look at having different dielectrics. So we know that there's going to be a layer or like a boundary layer of glass between the actual water and the capacitor. And we can use these same concepts as we have here on the calculations we did before, or use those calculations from before with these same concepts to remake our capacitance values. So now we'll get into the graphing. So our model responses and optimizations. This slide is just a brief intro into sort of the questions that we had going into this, because obviously we want to optimize capacitance, right? And this is the time we're going to do it because we can do all the number crunching together. We can create graphs, we can look at what the graphs are going to do, and we can account for all of these different variables. So the first test we ran, we just straight up ran capacitance without any separation, because that's a simpler and more robust calculation and equation, and it's less likely to have mathematical errors. And if we can optimize there, we might be able to optimize later. So let's start with those, and then later we'll take a look at what happens when you account for glass and separation. And I think those results will just speak for themselves. Okay, so we have the model response of capacitance with increasing dielectrics constants across 5 fingers. So 5 fingers will just be 5 pairs of these fingers, right? And we see that the capacitance increases pretty linearly as the dielectric constant increases, and this makes sense because our dielectric constant is acting as like a scalar component of our equation. And capacitance goes up from very low to very high, and the scary part about this is we have something like a 6 farad capacitor possible, and I'm not sure if I'm ready to be able to test that, but hopefully it doesn't come to that, and hopefully our true values in testing will be lower. Now we can measure something called capacitance versus finger separation. So the separation between each finger, or the width between the two plates, we wanted to see if you wanted the plates closer or further apart. And obviously from this graph, we can see that the closer the plates are, the higher the capacitance values. And the capacitance values here are obviously a lot higher than you would normally expect them to be, but we can expect similar results even for lower capacitance values. And then same thing here, we model the response with different finger widths. So now instead of changing the separation between the fingers, we change the actual width of the fingers themselves. And we find that the wider the fingers, the higher the capacitance. And obviously the capacitance here is also like really high, but I think that we can expect similar results for lower capacitance values with more things considered. And what we know here that's actually really interesting is if you increase the finger width and keep the spacing between the fingers, like the center of the fingers, the same distance apart, the separation actually decreases. So by decreasing the separation, you're increasing the width, and by increasing the width, you're decreasing the separation. And it turns out that both of these work together. So you can think of just making a capacitor that's as wide as possible with as little space in between as possible, should theoretically have the highest capacitance. Now, does this work for projecting fringe fields way past the glass? There's no way for me to actually tell, but if we just look at it like this, you would want really wide fingers and really low separation for high capacitance. And now we run this one more time, for the last time actually, to see what happens to our capacitance when we change dielectrics in between the paths. So like we go from glass to water, then back to glass, right? And so that means that the dielectric constant that's changing here is only changing a little bit at the top. And we can see that we start from similarly low values, but we don't go up nearly as high as values. And I think that for capacitance values, these are still pretty high. Normally you'd expect like microfarad or picofarad or nanofarad ranges, but I think this is a more realistic outlook, knowing that we only have an approximation that's not very realistic, and that's just the nature of the problem I decided to tackle. Okay. Having looked at the different capacitance values and looked at optimizing capacitance, and knowing that the PCB that we designed, that's our model, is already on the way and then we can't really change it, we then look at the circuit design. And this is going to be really important for sensitivity analysis to be able to measure capacitance. But when we actually go to integrate our design in, let's say, a vehicle, or let's say in whatever function it's going to be, there's a few different designs that we can make or that we should consider, and a few different functions that the circuit also needs to be able to do on its own autonomously. But before I go into that, I need to talk a little bit about the constraints that we had making this. So obviously there's a limited supply of microcontrollers, there's a global chip shortage. So I do have microcontrollers, and it would have been cool to run it on a microcontroller. I didn't really have a lot of time, and my microcontrollers are of QFN packages, and I'm not capable of soldering them onto my board with what I have available. FPGAs are out of stock, and the one I have is with a friend that's very far away, so that's not an option. So I ended up having to choose between an Arduino Uno or Raspberry Pi 2B, and I know that these aren't sort of the preferred methods because they both contain a lot of like external functions like EDCs and pull-up down pins and voltage regulation that normally you would include in sort of like an external circuit or on a circuit board. But with what we have and the time constraints that we had, we ended up picking an Arduino or a Raspberry Pi, and I have both of them, and we tested on both of them. It just depended on sort of where I was working and what I had to work with. And one thing that I actually didn't consider is that an Arduino and a Raspberry Pi are going to be a lot faster to prototype with, and that's because I don't have to worry about these things like ADCs and pull-up pins or pull-down pins, which I don't think I'll be able to use, but maybe if I have to measure really small capacitances, I'll be able to use. And if I was trying to measure these capacitances with the delays in shipping for my PCB, if I had to do this using a microcontroller or like an FPGA, I feel like there could be many issues that come up that I wouldn't be able to finish in time. So using an Arduino or Raspberry Pi does have a hidden advantage that it's faster to prototype with. And considering that our PCB is only a prototype, I think it's fair to say that this entire sort of design that I'll present later, once it arrives, is only going to be a prototype. And then that just means that the final circuit is a lot simpler than it would have been. That's fine, I'm okay with that. I'll make a complicated one day. And future packages or future implementations would be drastically different, and I'm also okay with that one. So our key design considerations for when we actually want to sort of, let's say, sell or market this product. We want to maintain heat around the sensor because we want to have this dielectric of water, not ice or snow. And a lot of cars have heating coils around the windshields already, so it would be totally possible to integrate with that with the car manufacturer, or we could include heating coils of our own if we wanted to use this, let's say, in our driveway to see how much water there was on our driveway, just to get a good sense of the weather outside while I'm working away in the basement. We want to be able to maximize sensitivity for capacitance range, and we can do that by tuning the sensitivity of the circuit, as I'll show you later. And we want this design to be robust and reliable. Cars go through a lot of vibrations constantly. Screws, a lot of times when you ship a robot in a car, it falls apart if you're not careful. So we need to make sure our design doesn't fall apart, especially with the shoulder joints and these little tiny components. So when we actually go to finally package this, that's something that you would have to consider and we'd have to test. And we also want the entire design to be slim. Now, unfortunately, with my design, I'm going to have many wires going everywhere. I'm going to have a breadboard. I'm going to have an entire Arduino sitting on my desk. But eventually, it would be possible, or it would be ideal, to put it all together on one PCB. And I totally think it's possible, or maybe even just two PCBs stacked on top of each other with some standoffs. And the last one is we want to consider if we are using AC or DC power, where we're getting our power, and how we're measuring the actual capacitance, because that's the entire design of the circuit. And we're going to get into how we measure capacitance now. So this is now sort of the end of the bulk of ECE 106, and this is the beginning of ECE 140. And we know that the capacitance time constant is defined as the resistance times capacitance. And it's the time taken for capacitor to charge 63.2% or discharge at 36.8%, like e to the minus 1. Now, in an RC circuit, if we know the voltage across the capacitor, we'll always be able to measure tau, because we can time how long it takes for it to decay or for it to charge or for it to do any of these things, right? So we can supply voltage from a completely discharged capacitor, let it get to 63.2% and measure tau, or we can charge to any voltage, just charge to half the original voltage and measure tau. not tau, measure time, not tau. Wow, I even left it in the slides. Measure the time it takes, and then we can do some math on it. And obviously, you can do the same thing, charging or discharging. Both ways work, right? Now, we ended up choosing, or I'm going to try and choose this method where we charge the capacitor to any voltage and see how long it takes for it to discharge. And I'm making this decision before I've had the opportunity to test this. I don't have actual capacitors at home for some reason. But there's a few reasons behind this. One is that I think this method allows us to charge the capacitor to full voltage, even if we wanted to anyways, and then we can measure it in the exact same way as before, so we don't lose any sensitivity if we need to. But it also means that we don't need to fully discharge the capacitor before starting or make sure it's fully charged. We can start from any arbitrary voltage and we can just let it decay to half the voltage, and then we'll be able to plug it into that formula with our time to get the capacitance. And that's adjusted to get half the voltage, just because getting half seems easier than getting a 0.3 something percentage. Okay, now our circuit design. This is the design I've chosen, and it's inspired by sort of the source-free RC circuit problem in ECE 140. So in ECE 140, you'll often have this capacitor and a resistor, and then you'll charge the circuit with a switch, and then all of a sudden the switch will change positions, and it'll just be the capacitor and the resistor, right? And in this case, the capacitor slowly discharges through the resistor, and we can time how long the voltage takes to drop, and we get our time constant, right? So that's where we got the inspiration from. This design shown here is my own model I made, and I apologize for the maybe for the colors, but my program did this and I don't know how to change it. But we have a VCC pin, which is going to be essentially the same thing as a switch from our circuit problems, ECE 140. We have our sensitivity line, which is going to be measuring the voltage drop across the capacitor and the resistor. They're in parallel, so it should be okay. And then we have our ground pin, which is going to ground the capacitor and resistor and allow us to measure the voltage across them. Hopefully that makes sense. Hopefully it works out when I be able to test it. And maybe if something happens where this doesn't work out, I'll come back and make amendments to my slides and introduce you to my new methods. And then we get to our overall circuit design. On our Arduino, we're using an Numerical 32A chip. That's just what it is. And we have an input-output sensitivity of 0 to 5 volts. And in future designs, this is definitely going to have to be regulated. On our Arduino, it might even have to be regulated just because it's really difficult to get steady voltage out. But hopefully it'll be okay, and hopefully we can use the voltage. And then we have other digital pins on the Arduino, which is sort of is what it is. And this isn't super important right now, but in future designs, you would want to split power out of the different banks just because you don't want to fry one fuse inside the chip. And there's no power splitting circuit, which again, we might want to have, especially if we're taking USB power, but it is what it is. And then we have in our diagram this data output that's analog, but we could have this data come out in any way, shape, or form we wanted. It makes no difference. And we have the same diagram that we had from before, just with now a true ground. Okay, so that's the circuit design. It'll include all of these cool fancy things like heating coils and data and sort of interfacing with your wipers or whatever that I'm not going to show you. Now, we get into our preliminary sensitivity analysis, and it's hard for me to say what the true sensitivity is going to be without actually knowing the capacitance, because I know that my capacitance is going to be different from what I calculated previously, especially since I have really large capacitances calculated previously, but we'll try our best. So there's a lot of different influencing factors for our sensitivity analysis, like the thickness of glass, the quality of the traces, and the design of the traces that we explained previously. But we know for sure that slower discharges is more accuracy, but we get less frequent updates, and a fast discharge is going to be less accurate, but we have faster updates. And this is going back to what I said before, is a lot of times maybe you're going to want to choose one or the other. So in a car, I want my wipers to update fairly quickly to changes in the environment. But in, let's say, my driveway, we can have a slower discharge. I just need to know if there's ice on my driveway when I leave in the morning, right? And that can be something that updates like once every 10 minutes, 15 minutes. It's not as much of a big deal, especially since ice accumulates pretty slowly. And then we sort of take a look at the highest possible accuracy on Arduino. 62.5 nanoseconds. We're not going to run it that fast. We're going to run it with microsecond precision just because it's easier and we don't need to use digital pins with like a specific circuit, but we could run it that fast if we needed to. And we also know that we're taking analog readings, or we're actually using Arduino's inbuilt analog digital converter, but we're taking analog readings, and these take a lot longer than digital readings do just because of how it works. And so we come again to this sort of game of balance between reading accuracy and timing accuracy. And hopefully I get this game of balance right. So for what it's worth, I think our limiting factor is going to be timing. Just because we're going to always be able to read around 2.5 volts pretty consistently. And the biggest issue is going to be able to have the time to read that value. And I think this is the same to a lot of other robotic applications. You're looking more so at the time it takes to read a value than how often you're able to read a value, because how often you're able to read a value and update that value depends on how often you can read from the sensor. So we're going to be constrained by timing, and we're going to be trying to target less than 60-second response times, so a minute to respond. And this could be a lot slower, it could be a lot faster, it depends on what the actual capacitance is. But if my capacitance is anywhere near where I calculated before, 60 seconds might not be enough. And we're going to have to choose a resistance for some R. And since I calculated large capacitances before, I'll use small resistors now just to help keep the time constant down. But when we actually build the circuit, we might find that our capacitance is a lot lower. And I'm expecting it to be a lot lower, especially when we have no dielectrics present. And so then we might need a larger resistor to bring our time back up to something that we can measure. So this is the approach that we're going to take when we look at how to optimize our sensitivity. And there's two slides I want to show you. So there's this one here, which is the voltage decay with a 10 farad capacitor, which is a very large capacitor, but it's an average of what I calculated earlier. So we'll have to work with it. And this is in a source-free RC circuit and calculated the same way we did in ECE 140. So we know the lower resistor equals a faster decay, but we only really can't go so fast. Like if we look at this 5 voltage to a 2.5 voltage drop, the fastest drop we have is somewhere around 60 seconds, which is already the upper limit for what we set, and that's using a 10 ohm resistor. So hopefully we don't have 10 farad capacitors, but we know that we will remodel this once we get a better handle of what the actual capacitance is like, because so this is one graph we can use to quickly examine and quickly sort of determine about how much resistance we want in our circuit, because we can really quickly see how the voltage will decay with different capacitances. And the other graph, which I like a lot more, we use this graph to determine the time it takes for our voltage to decay to half of what it was originally, which is, again, remember how we're timing our circuit. And we can then model this for different values of resistors. So remember from before, the previous slide, I can't go back in the presentation for some reason, but from the previous slide, our 10 ohm resistor was the one that showed the curve. All other resistors look linear because it takes so long to decay. And the 10 ohm resistor is the one that decays the fastest. And you'll see the same trend exists in this slide. The 10 ohm resistor is the fastest decay across all capacitance values, and by quite a large margin. And you can see for larger resistors with large capacitance, we're using a 10 ohm capacitor, a 10 farad capacitor here, it can take like 3,000 seconds to decay, which is crazy. Like that's a really long time, right? So we use this kind of graph. I think it gives me a better representation of how strong of a resistor I want to use when calculating my capacitance. And we will redo this graph for smaller capacitances now, but I don't know how small we need to go. So we'll do it for about, I think this is either 1 to 5 microfarads or 0.1 to 0.5 microfarads. I don't remember exactly. It's 1 to 5 microfarads. Right, okay. So this is a timing diagram that's, I think, more realistic to what we're looking at, because now our time values in terms of seconds are closer to microseconds, or milliseconds, microseconds. And And this starts to like bring in the issue of like our timing constraints. And obviously we can see that if we use larger resistors, the time it takes to decay with varying capacitances goes up. So once we get a rough ballpark of the sensor design with like one capacitor or one resistor, we can remake this graph and we can find the ideal balance of resistor to use. Maybe not for our prototype, but in the future, because maybe I don't have the specific resistor that we would want or the means to build it. But we can redo this sort of graphed analysis to say, okay, what is the maximum time of decay I have? And what is sort of the maximum capacitance range I have? And we can determine this operating window and we can optimize the resistance to get us the most difference in time that we can actually allow. So we can use really large resistors to get a really long decay to get a lot more accuracy. Or we could use a medium-sized resistor to get a medium-sized decay. And maybe that's exactly what we're looking for. So this kind of thing, I really like this graph. And I hope I talked about it in a way that you can understand and understand and realize what it's for. Okay. So now we go on to sort of a rough detection limit. So if we have time down to 1 microsecond, which if we look at the graph from before, it was in microseconds. So 1 microsecond precision with a 100 kilo ohm resistor, then we technically have some pretty okay precision. So yeah, that's the preliminary detection limit that we have. But obviously this is going to change depending on maybe the voltage fluctuation of the reading, because we don't know what might happen, and I don't know how the voltage fluctuation might affect the reading, especially if the reading is going to be maybe plus or minus 0.1 volts on our step difference from 0 to 1023, and how much that will change our capacitance values, because if it reads one step too early by a microsecond, then we're losing an entire unit of precision, but that's fine. Unit as in like one of the 0.0144, not like an actual unit of precision. Okay. Now, this should come after I've designed and built the circuit, but I'll give it to you now and then I'll give it to you again at the very end. So if you want, you can skip it the next time I show this to you. And yeah, let's just do this now. So the first thing is the capacitor design. Now, it was really fun to try and figure out solutions to this problem. Unfortunately, it required a lot of math and a lot of brain. And it would be really cool if there was a way to make a computer help me with the math and the brain in terms of a simulation. And we have seen that there are a lot of different simulations for coplanar capacitors or even fringe fields. Maybe not necessarily in terms of direct capacitance. I know for, as I mentioned earlier, coplanar capacitors or coplanar plates, a lot of it's for like waveguides or signals. But there are definitely ways that we could simulate this, and maybe I should have learned MATLAB to simulate this. But in the future, I would definitely try to do that. And from what we can tell, as I mentioned earlier, we want to increase area and decrease separation. And this might not always be the best choice to create fringe fields, but I don't know how to calculate that. So in the future, either try and maximize and see what happens, run multiple prototypes, or simulate something, or maybe all of the above, right? And then the last one is that I would like to be able to design for measurable changes in capacitance. I don't think 1 farad to 15 farad is a measurable change in capacitance, but I do think maybe, let's say, half a farad to 1 farad is more manageable. But ideally, I think most capacitors are, again, nanofarad to microfarad range. So it would be nice to be able to confidently say that our capacitor is going to work within the range without having to just say it should. Okay. Next slide, circuit design. So I talked about a lot of these in the foreword, so I won't spend too long on it anymore. but we want to use a lot of these individual circuit elements that we could, source and integrate onto like a circuit mount, like a surface mount board. And one thing I sort of touched on earlier is we might want to have methods of filtering and smoothing the output signal, because we might have fluctuations in our input and we might have like differences in sensitivity, but if we're measuring enough times each second, we could totally have like a weighted average or a Kalman filter or something similar along these lines to help reduce the error on our output. And this depends on obviously where the sensor is being used. If it's in a car, we probably want the sensor to do this, or we want some element of the car to do this for the sensor. But if it's being integrated in a different design, we might have different requirements. So this depends on how we're integrating the entire device, but it is worth considering, and it is something that could actually improve the, let's say, sensitivity or accuracy of the sensor. All right, now really quickly, cost analysis. We are actually like the premise of this is we want to design something that eventually would be put in a car, because this was the problem that we came out to solve. And a big limiting factor of different devices from being put in cars is cost, but we can confidently say from here that it's going to be pretty inexpensive to put in a car. The only thing that might be really expensive is a microcontroller, because there's a current global shortage of chips. But once that's over, I'm sure it'll go back down to be like $2 per microcontroller, and it's definitely a very affordable option for vehicles. And this doesn't really super matter much for an actual project, but it's just something that I wanted to note. All right, the last slide, the built-in test sensor with response graphs. I've mentioned this many times, it's not here yet, but soon I'll give you your most fabulous slides that you're going to look forward to so much. So thank you so much for listening. I talked for a long time. I apologize for any audio issues. I had a lot of fun doing this lab. I learned many new things, especially about maths, and I hope you had at least some amount of fun listening to me talk about my project. Thank you. Bye-bye.